Hi guys, it's Kate, and this video is about how to find the distance between two lines. These distance formulas are sometimes tricky to keep track of, especially when you're memorizing them as separate things. Hopefully this video will take you a step in the right direction, away from memorization and more towards understanding where these formulas come from and why they're important and when to use them. So, finding the distance between two lines. There are three basic scenarios for two lines to coexist in R3. One of them is intersecting lines. The second is parallel lines. And the third, most complicated instance is skew lines, where the lines are neither parallel nor are they intersecting. When you're given two equations for two different lines, the very first step is to figure out what relationship the lines have to each other. How do we do that? Well, first things first. When you take a look at the two different equations you're giving, let's call these lines L1 and L2. We can extract the direction vectors for each line by extracting the coefficients on the parameters in each of their parametric equations. Once we've done that, we take a look at them. If v1 and v2 are scalar multiples of each other, then we know that the lines point in the same direction, and we're dealing with parallel lines. Or v1 can be written as some scalar multiple k of v2. The most important thing to realize about parallel lines is that they stay the same distance apart forever. That's the idea of being parallel, of course, but reworded or reconceptualized for use in this particular type of problem, it's important to see that that means that any point on this red line is the same distance away from the blue line. It doesn't matter if I'm looking at a point here or a point here, the distance to the blue line is the same. And so what you're actually dealing with, computationally speaking, is no different than the distance from a point to a line. Simply choose a point along the red line, literally any point at all, and compute the distance to the blue line. So the way to solve the distance between parallel line problems is to simply choose a point on one line and compute the distance to the other line. I have a separate video on how to find the distance from a point to a line, and you should definitely refer to that if you're feeling fuzzy. So this is no different than actually just simplifying it down to point to line distance formula. Now, the second question that needs to go through your head is maybe they're intersecting lines. You've tested to see if they're parallel, they're not. The next type of test you should do right off the bat is to see whether they're intersecting lines. Now, when two lines are described, L1 and L2, sometimes they're described using the same parameter. You'll see a T appear in L1 and a T appear in L2. And in this moment, it's really important to say, nope, I'm going to change the name of the parameter for each different line so that each line has its own parameters. So here I've already done that. T is the parameter in L1. S is the parameter in L2. Now, when we're asking whether lines intersect, what we're really saying is, are there specific values? Is there a good choice for T and a good choice for S such that the X component, the Y components, and the Z components of both of these lines equal the same thing? I.e., is there a value for T and a value for S such that these position vectors point to the exact same point? That would be a point of intersection for these lines. And the exact way to do that is simply by taking these two component functions and setting them equal to each other. Here's what this system of equations generally looks like. Now remember, this is what these line equations look like in their most general form. When you're given two actual examples of lines, x1, y1, z1 will be the point that L1 goes through, a1, b1, c1 will be the direction of L1, x2, y2, z2 will be a point on L2, and A2, B2, C2 is the direction of L2. So all of these variables with subscripts will be actual values that are filled in. The only variables that retain letter form are the t and the s, the parameters within the component functions. So what you end up looking at over here is if you look at just the first two lines here, the x component and the y component, what you end up having is a system of two equations with two unknowns. Go about solving that algebraically for t and s. If it happens to have a solution, go ahead and plug it into the third equation to make sure that it holds for z as well. If it does, that means that the lines are intersecting. And of course, the distance between intersecting lines is 0. Now, you've quickly tested to see if the lines are parallel. They're not. You've tested to see if the lines are intersecting. They're not. They must be skew. Skew lines are neither parallel nor intersecting. They're just two lines that fail to intersect and they're not pointing in the same direction. Here's an example of what they look like. Now, let's label a couple of important points on these lines that you can find just by looking at their equations. And of course, for L1, I'm talking about the point that that line goes through, x1, y1, z1, which I'll call P1, and the point x2, y2, z2, which is the point that L2 goes through, which I will call P2. I'm going to label these on either of these lines. The other thing that you can tell by inspection is the direction of L1. It's going to be the coefficients on T, A1, B1, C1, and the direction of L2, which is going to be A2, B2, C2. I've named these direction vectors V1 for the direction of line 1 and V2 for the direction of line 2. I'm going to draw them into this drawing as well. Now, let's visualize exactly what we're trying to solve for. We're trying to solve for the distance between these two skew lines. Now, the way I've drawn this sort of lacks depth perception, so it looks like these lines might intersect right outside of where we're looking at them, and they don't. There should be some depth to the lines, like maybe L1 is pointing at us and P2 is more perpendicular, going left to right, east to west across us. The key is that what we're looking for is this, the distance between the skew lines. And I would really encourage you to sort of set up two skew lines and find the place where they are closest together. And you'll find that the important trait about this distance measurement is this path, this white dotted line, happens to be perpendicular to both lines themselves. I tried to draw in a little perspective there so maybe you can get some depth. But what's happening there is very interesting. That the path we want to measure, the place where we can answer this is how far apart the lines are, which is happening at their closest point to each other, that path is going to be perpendicular to either line, and that is the major key. The way that we go about tackling this is we take a look at P1 and P2 and we construct the vector that connects P1 to P2. Now, it would be only through completely blind luck if we actually happen to pick a P1 and P2 such that these already were the two closest points. And if we happen to, this formula that we're about to talk about will work anyway. But the important point to note is that this P1, P2 vector, this green guy, is more often than not, is not the shortest distance between the two lines. So here's our vector, and what we want to do is we want to project it onto a vector that's pointing in the same direction as our white dotted shortest path here. Now, how do we find a vector that is in the direction of this white dotted shortest path? Well, note, we remember that this white dotted shortest path is perpendicular to both V1 and V2, so the way to find that vector is to cross V1 and V2. Once we cross V1 and V2, we now have a vector that is perpendicular to both lines, meaning it's going to point in the same direction as our desired white dotted path. Then we take this vector, P1 to P2, that is not along the shortest path, and project it onto this vector that is along the shortest path, and it will give us the total distance of this white dotted line. And so the formula for finding the distance between skew lines is simply that. It is the projection of this green vector that connects the two lines and not necessarily along the shortest path onto this vector, which is pointing in the direction of the shortest path. And there you have it. These are the three different types of approaches for finding the distance between two lines. We've discussed them in the order that you should investigate because we've discussed them in order of complexity. You can tell upon inspection whether lines are parallel, in which case you can just boil it down to a point to line formula. If your lines fail to be parallel, your next step should be to use a little bit of algebra to see whether the lines are intersecting, in which case the distance between them is 0. And then if both of those fail, you know you're dealing with skew lines, in which case you need to apply this projection formula, where you take this vector that connects one line to another, but not necessarily along the shortest path, and project it onto the vector that's pointing in the direction of the shortest path. That is the cross product of the two direction vectors of those lines. Most of the time in a lot of problems you'll be told straight out whether lines are parallel, skew, or intersecting, but in the event that you're not, this is how you should tackle those problems.